Hi everyone, welcome to the topic of job performance and value. During class we had two team presentations looking at the relationships between task performance, organisational citizenship behaviours and career outcomes. You also had a self-test on utility analysis, which I know you loved. I have posted both the test and solutions on LMS under week 10. Next we need to discuss utility analysis in relation to job performance and value. This formula on the slide is from Cascio and Boudreau on page 214. Note that they have specified two different N terms. The first N is the number of cases accepted, such as selectees. The second N is the number of cases processed on the predictor, such as a recruitment and selection procedure. The second N is there solely for the estimation of costs. Also notice the multiplicative relationship between the standard deviation and validity. If performance differences between individuals are large, so that the standard deviation is large, even a predictor of relatively low validity can give the same results as one of high validity would with a lower variability in performance. Cascio gives the example of a procedure with a standard deviation of $10,000 and R equal to 0.25, having the same value as one with a standard deviation of $5,000 and an R of 0.5. Excuse me, all other things being equal. So for greater standard deviation, the payoff from increases in validity of the program will be greater. Let me just note that this model assumes a constant or non-dynamic standard deviation, and I just need to flag that for later consideration. Before we go on to discuss the impact of turnover, we need to consider one of the key concepts throughout the Cascio and Boudreau text, and that is pivotal talent pools. You'll find the idea of pivotalness of employees mentioned before in the textbook on page 84, and this foreshadows material later in chapter 9. Just as we brought some material forward from chapter 8 in week 2 on utility, today we'll bring some material forward from chapter 9 because we need to look at these concepts now. To help us identify pivotal talent pools, we first need to introduce the concept of performance yield curves, and we have talked about this before. Here on the slide we have two performance yield curves for two roles at Disneyland theme parks. Using the example of Mickey Mouse and sweeper roles, an example from Boudreau and Ramstad, we can see the impact of changes to performance on strategic value for these two roles. It is important not to confuse importance with pivotalness. Both sweepers and Mickey Mouse are important, Mickey Mouse more so. However, the role of Mickey Mouse is not necessarily pivotal. Mickey Mouse's performance is very important, as shown by the high curve in the diagram on the slide. However, the variation in job performance between the best Mickey Mouse and the worst Mickey Mouse is small. This is shown by the flat line on the curve. On the left side, where the line is dotted and the curve falls dramatically, this shows the impact of Mickey Mouse perhaps harming a customer, for example, which would be a strategic disaster. Therefore, there is little payoff from improving the performance of Mickey Mouse once the person has met the high performance standard. On the other hand, for the sweepers, the curve is much steeper than Mickey Mouse, indicating that variation in sweeper performance creates a greater change in strategic value to the organisation. The sweepers make pivotal differences in Disney's strategy of being the happiest place on earth. Also, we might even want to look at identifying the strategic value of tasks within roles. Here we can see that sweepers are involved with guest relations, such as giving customers directions, and sweeping, but it is the guest relations role that is pivotal. Performance variations occur for two main reasons. One reason is the nature of the job, and in particular the amount of autonomy or discretion a person has in a job. When jobs are rigid and specify exactly how the job needs to be done, differences in individuals' ability and motivation have little impact on performance. For jobs with a lot of discretion, variation in ability and motivation in individuals can result in large values of the standard deviation in those jobs. Standard deviation also increases as a result of job complexity, as complex jobs mean that it is more difficult to specify the behaviours needed to complete the job. A second factor that influences the size of the standard deviation is the relative value of variations in performance. Next, we will compare McDonald's to Starbucks in relation to this. McDonald's and Starbucks have different strategies. McDonald's is about consistency and speed of service. As you know, most tasks at McDonald's are automated. This is very different to Starbucks, who pride themselves on their diverse and multi-talented baristas. These baristas are given a wide latitude in how they serve customers, and you can see this on the slide in terms of both companies. First, let's look at McDonald's. As you can see, they are risk averse. Their distribution of performance is steep, representing the high organisational value of their average performance level. This curve is also very thin, showing that the performance of employees does not vary a great deal and is tightly clustered around the mean. On the other hand, Starbucks has a very fat and flat performance distribution curve. Due to their strategy that they have a large distribution in terms of job performance. Because they allow employees greater discretion to perform their job the way they like, they have a wider range of performance, with some people performing at the lower end and probably disappointing customers, and then other employees performing at the top end of the range and delighting customers. Then looking at the value of performance across the two companies, this is the dotted line on the diagrams, Starbucks really values their high performers and as a consequence has to accept that there is a risk in allowing employees this discretion in their jobs, and therefore there will also be low performers. McDonald's, on the other hand, standardises tasks and therefore performance only needs to meet these expected levels to be valued. What can we do if we can describe the variation in individual performance? What good is that to us in HR? Some possible answers are that we can reward differentially, we can train and develop to get improvement, and we can place employees appropriately in jobs suited to their skills and skill sets. Let's focus on that last one of placing employees. We would actually want to be able to predict their skills and skill levels before we place them, not to have to place them and then wait to find out whether they have the appropriate skills for the job. Predicting job performance of applicants for selection is one of the main things we need to do well in HR. The possibility of a relationship between predictors of job performance and actual job performance is where we started off in week 2 of the course, when we were starting to look at analytics, and it's really at the heart of the utility model. The role of variation in performance, or the standard deviation of performance, is in that utility equation. Can we predict performance by measuring some indicator of it? The idea of prediction is at the heart of HR analytics, and performance management systems often have predictive uses. They are not only predictive, performance measurement can be used for the purpose of giving rewards for past performance, which is not a predictive use of them. To date, probably our best indicator of future performance is cognitive ability. We are not just talking about IQ measurements here, although the SAT and Armed Service Vocational Aptitude Battery are related to IQ. Arneson et al. Wanted to show that for cognitive ability tests and their relationship to job technical proficiency scores in the case of Project A data and to scores at universities such as first year grades and GPA, that there's a linear relationship, or at least monotonic increasing. This is because some people have argued that much of the money invested in psychological testing is not necessary. When we are dealing with applicants who have resume credentials that show that they are already doing rather well, for example, they have verified good results at school or university and past success as shown by good references. Further testing will not gain us anything in prediction. The researchers cite Malcolm Gladwell and others who have argued this. Arneson et al. Review the past research and its problem in not being able to test the relationship at the top end of the range. That is why they look at very large data sets. Arneson et al. Wanted to show that even when there are two applicants who both get over the basic qualifications, experience, and references hurdles for a job, testing that detects differences in required knowledge, skills, and abilities will be related to differences in performance. The course and methods for assessing applicants do weed out the lower half or more and leave us with the upper end candidates, so they were particularly pleased to see that at this upper end, the relationship between predictors and job performance not only holds up, but it's even stronger. That finding is interesting, and we will come back to a similar point later. These are the plots of the 4 large data sets they analysed. The curves are not regression lines, they are Lowe's curves, locally weighted scatter smoothing. Lowe's curves are a statistical technique for fitting a line to data regardless of its underlying shape, if there is one. So it is not forced to be straight or quadratic or any other function in particular. This technique is very useful for exploratory and descriptive procedures. There's a lot of data represented here. They show that the relationship is monotonic increasing, and where it is a curved relationship, it actually curves upwards at the higher end. It certainly doesn't flatten out. Look at these curves. It looks like there is a lot of predictability here, doesn't it? But the Loeb's curves cannot tell us this, so Arneson et al. Fitted regression models. And they get significant fitting models, which is not surprising with the large amount of data. Here is their table of regression coefficients. Please note it's not reported in the normal way, but that's not really important. These are the linear regression coefficients. If we look at the standard errors for the coefficients, we see that they are tight, meaning that they are quite good estimates. Again, this is not surprising given the large amount of data. For example, in the top row for the Project A column, an increase in 1 on the predictor is associated with an increase of 0.459 on the criterion. If we look back at the graph, both the horizontal and vertical axes for Project A are in standard score units. So that looks like a pretty good coefficient, doesn't it? It looks like pretty good at being predictable. If you increase 1 unit on the predictor, you get an increase of almost half a unit on the criterion. That's what it's telling us. A nice slope there, and it looks pretty good. We're going to come back to this study later, but let's digress for a minute and look at Sawyer and Hogarth. So here you can see on the slide, Sawyer and Hogarth 2012. Does the manner in which results are presented in empirical studies affect perceptions of the predictability of the outcomes? Noting the predominant role of linear regression analysis in empirical economics, we asked 257 academic economists to make probabilistic inferences based on different presentations of the output of this statistical tool. The questions concern the distribution of the dependent variable, conditional on known values of the independent variable. The answers based on the presentation mode that is standard in the literature demonstrated an illusion of predictability. The outcomes were perceived to be more predictable than could be justified by the model. In particular, many respondents failed to take the error term into account. Adding graphs did not improve the inference. Paradoxically, the respondents were more accurate when only graphs were provided, that is, no regression statistics. The implications for our study suggest the need to reconsider the way in which empirical results are presented and the possible provision of easy-to-use simulation tools that would enable readers of empirical papers to make accurate inferences. So what does all that mean? So really the title of the article gives it away, The Illusion of Predictability, How Regression Statistics Mislead Experts. Sawyer and Hogarth are concerned about researchers over-interpreting predictability based on regression statistics. They tell us to be very careful about how we interpret regressions and correlations. I will not describe their study in detail, but briefly they presented some example regression results to people who should know about these things, like economists and some statisticians, and asked them some probing questions about the resulting predictability that could be inferred from the regression statistics. The experts' intuition were generally not good. They thought the regression statistics were showing more predictability than they were. And I should note that we would probably make the same mistakes. The point is that these experts were not incompetent, far from it. The point is that it is hard to get your head around, and we tend to fall back on routine ways of doing interpretations and relying on the assumed implications of the analyses. Regressions are about predictability, so we look for and expect predictability. Since analytics is our focus here, we need to understand this. Validity coefficients are essentially regression coefficients. Like these experts, we will tend to focus on the uncertainty of prediction in those regression coefficients erroneously. If we go back to Arneson et al., remember we said that the regression coefficients looked pretty good, and there was very little uncertainty about those regression coefficients because of the large amount of data. But now let's look at the fit of these models. They ran two models on each dataset, one model with just a linear term and one with a quadratic term added. That was to see if there was curvilinear relationships in the data. Let's look at the part of the table for the full data. They reported the R-squared for the model, that is the fit of the model. At best, which is in Project A, it is 0.20, accounting for 20% of the variation in the criterion. That is not very much. In the other datasets, it's even lower. And in the data at the top end only, it is minuscule. For most management and professional jobs, it is that top end where we are operating. The point of the Sawyer and Hogarth article is that curves and regression coefficients can be very misleading because we see predictability that simply isn't there, the illusion of predictability. Sawyer and Hogarth tend tell us to look at scatter plots, and this helps to reduce this illusion, but of course we don't usually see scatter plots in reports. Most validity studies do not report the SER, the standard error of regression, at all. That is the predictability of the dependent variable, which Sawyer and Hogarth tell us is essential information. So far, there are 3 summary points I want to make from this. Evidence-based HR can take a lot of data. Arneson et al. Had to use large data sets to try to establish that there is a relationship between widely used testing and the outcomes that testing is supposed to predict. It is not trivial to accumulate that kind of data. Second, they've succeeded in showing that the relationships are monotonic increasing. That is quite convincing for me in the graphs, and with that research literature to draw on, it provides the evidence we need. We do not have to all go out and collect such evidence for ourselves. Number 3, we are suffering from the illusion of predictability if we think that there is much predictability in those relationships. There is not. Next, a study by O'Boyle and Iguanas 2012. We revisit a long-held assumption in human resource management, organizational behavior, and industrial and organizational psychology that individual performance follows a Gaussian normal distribution. We conducted 5 studies involving 198 samples, including 633,263 researchers, entertainers, politicians, and amateur and professional athletes. Results are remarkably consistent across industries, types of jobs, types of performance measures, and timeframes, and indicative that individual performance is not normally distributed. Instead, it follows a Paretian power law distribution. Assuming normality of individual performance can lead to misspecified theories and misleading practices. Thus, our results have implications for all theories and applications that directly or indirectly address the performance of individual workers, including performance measurement and management, utility analysis in pre-employment testing and training and development, personnel selection, leadership, and the prediction of performance, among others. So isn't that interesting? So one possible reason for the low predictability of those relationships is that the distribution of performance is not normal. Far from it. Let's have a look at the distribution of performance in more detail in the Boyle and Iguanas article. In research and practices based on research in HRM, the distribution of performance is always assumed to be a normal distribution. Why? Prior to the days of computers, a lot of statistical techniques involved laborious calculations. Some of the properties of the normal curve made it useful for those calculations. It was probably natural that then the early researchers on human performance assumed that human performance would be distributed as the normal distribution. As a result, performance management systems have procedures for training away the rated biases of leniency and severity, and forced distribution rating scales are used in performance measurement. Those practices can only be defended if there is some basis in truth. Otherwise, they produce fabricated distinctions between people that affect their lives. How can employees work and aspire to performance in a distribution that is made up and does not reflect the reality of how their performance is actually distributed? At this point, stop and have a think about it. Think about job performance in your workplace. Is performance normally distributed? Are performance ratings normally distributed? If not, what does the distribution look like? Have a go at sketching this. O'Boyle and Iguanas contend that the distribution of performance by humans is distributed according to a power law. That is, it is a Paretian distribution. The schematic diagram shows that these are definitely not the same shaped distributions. Depending on the chosen parameters, the power law distribution will have different shapes. It does not always look like this one. O'Boyle and Iguanas present 5 studies using large amounts of data in each and many different instances to show that the distribution of performance is Paretian. They used a fitting procedure to show that the fit of the Paretian distribution was vastly superior to that of the normal distribution. Now, they have used the most objective performance measures that they could. They specifically avoided standard performance ratings by supervisors because those have usually undergone training in which they are told what kind of distribution is expected. We might be left with the question of, if we could do this with unbiased performance ratings by supervisors, would we get a normal distribution? The answer is no, we would not get a normal distribution, which is why performance management systems have extensive training for raters, because if they were left to their own devices, we get bunched up distributions, more like the Paretian, but often the other way around in ratings. that is with the high point further to the right, referred to as leniency bias. Now let's discuss the implications for utility analysis. Utility analysis relies on the assumption of normality on the criterion, which is often individual performance. You can see this in the formula with reference to the Z-score and net standard deviation. Do you remember when we looked at the simple version of the utility formula? We said that the great discovery of the Brogden-Cronbach-Gleason model or approach was that we could work out how big a gain we would get on the criterion for a given difference on the predictor. So therefore, utility analysis will not work without the assumption of normality being met. O'Boyle and Iguanas present some other implications, but they are not so relevant to us here in our HR analytics consideration. Now we've got an article by Beck, Betty and Sackett 2014, where they say, in a recent article, O'Boyle and Iguanas 2012 argued that job performance is not normally distributed, but instead is non-normal and highly skewed. However, we believe that the extreme departures from normality observed by these authors may have been due to characteristics of performance measures used. To address this issue, we identify 7 measurement criteria that we argue must be present for inferences to be made about the distribution of job performance. Specifically, performance measures must A. reflect behaviour, B. include an aggregation of multiple behaviours, C. include the full range of performers, D. include the full range of performance, E. be time-bound, F. focus on comparable jobs, and G. not be distorted by motivational forces. Next, we present data from a wide range of sources, including the workplace, laboratory, athletics, and computer simulations, that illustrate settings in which failing to meet one or more of these criteria led to a highly skewed distribution, providing a better fit to the data than a normal distribution. However, measurement approaches that better align with the 7 criteria listed above resulted in a normal distribution, providing a better fit. We conclude that large departures from normality are in many cases an artifact of measurement, so they're challenging the result of O'Boyle and Iguanas. So why did Beck, Beatty and Sackett find normal distributions of performance when O'Boyle and Iguanas found power law distributions of performance? Look, I don't have a clear answer for this question. For some of their data sets, it may be because they are using averages as a data input. The central limit theorem tells us that the distribution of the mean approaches a normal distribution for samples of around size 30. So, but not for aggregates from power law distributions. So it's maybe partly the answer. I think the answer lies in the type of data they've used. So in page 540 to 42, they state that the work task was done in a laboratory. They say that their measure is aggregated over 10 trials per block. And near the bottom of page 540, they appear to be saying that the performance was on a block was used, although it's not really that clear. On page 541, looking at a call center example, they said that the data appear to be average call handling time per employee, and as such it also appears to be means, and the distribution we're looking at really is the sampling distribution of the mean, which we would think would be normal. On page 542 of their article, looking at the National Hockey League, they say they compiled data from 2005 to 2006 and 2011 to 12 seasons. They do not say what they did specifically. Perhaps they also averaged for their players across the seasons or aggregated. It doesn't matter. If the denominator is the same for all, then a total is likely to be an average. But to aid in this confusion, Iguanas and O'Boyle have come out with a further paper in 2014, which produced even more power law distributions. And they're drawing some conclusions from there, which you can read on this slide here. Okay, so this is from the top panel of Figure 3 in Iguanas and O'Boyle in 2014. One interesting conjecture they make is about the relationship between individual performance and the value to the organisation. Remember Boudreau and Ramsted's performance yield curves from earlier in the course and earlier in this presentation? Here are the examples of performance yield curves. The straight line for the sweepers is what we are looking at here, using the example of Mickey Mouse and sweeper rolls at Disneyland theme parks. The performance yield curve is an example of an analytics method in this context, a standard procedural way of analysing a problem and coming up with an answer. So Iguanas and O'Boyle are saying that the straight line for the sweepers is often not a straight line for those kinds of workers. It is not a straight line where the power law applies, according to these authors. And do you remember the distinction we made between the sweepers and the person walking around in the Mickey Mouse outfit? The behaviour of the Mickey Mouse person was already very tightly controlled because it was critical, but the behaviour of the sweepers when talking with guests is also critical to delighting them. That mission of delighting theme park guests is the core mission of the Disney theme parks. This is the lower panel of Figure 3. Iguanas and O'Boyle also make the distinction between the relationship of performance to strategic value for different levels of proximity to the core mission of the organisation. This is why they are talking about star performance, because there is a lot of value to be had. Finally, one of our important topics from earlier in the course was turnover. The usual relationship between job performance and turnover is a U shape. At the lower end there is encouragement to leave, and at the higher end there is dissatisfaction and a need to leave to get on. For just voluntary turnover, the lower end often cannot leave because they do not have many job prospects. That is the dotted line on this slide in Figure 4. At the high end of performance, the compensation system based on a normal distribution does not give sufficient recognition and reward for outstanding performance because the distribution is actually the wrong one. If the reward system was based on the power law distribution, then the high end would be rewarded appropriately and would not leave. That is the solid line in the figure. It is not clear how they get the lower end to rise, though. I'm a bit worried about what this implies. At least in Australia we have the minimum wage system. And of course, Iguanas and O'Boyle would tell us that turnover at the low end is not a problem anyway, as most of the value is coming from the higher end. Unfortunately, though, costs associated with turnover are not just about lost value. Okay, back to utility analysis and the formula. The biggest difficulty is using the formula is estimating the standard deviation on the criterion. It is theoretically the standard deviation on the criterion for all cases, including those who have not been treated under the particular HR program. For selection, it would be all applicants, but as we would already be using some selection method and would not resort to random selection, standard deviation in this case applies to those under the existing treatment or selection program, that is, existing employees. So standard deviation can be estimated concurrently on existing employees, and we've discussed this previously. So the value for standard deviation used is in practice an underestimate based on the standard deviation for existing employees. Still, standard deviation has to be estimated, and there are various ways of doing this. You'll see 6 methods on the slide. These are discussed in detail in your textbook. So it's not important for the exam, at least, that you know each of these methods in detail, but if you do go about doing utility analysis in the workplace in relation to job performance, you will need to know which method to select to determine the standard deviation. Lastly, in terms of process, it's important to accurately predict the standard deviation of job performance, as the impact of this value, is multiplied in the utility equation. But on the other hand, you may need to consider which method will be seen as more credible to management. Another important aspect of estimating the standard deviation is that it identifies the talent pools with the greatest performance variation, and therefore identifies groups which create the largest strategic impact. Lastly, I've just made a note there that we need to be careful about communicating the impact of the utility analysis. And I ask you a question. As a manager, how would you react if you were told the following? The payoff from a selection program is more than $105 million. Now the workshop that we were going to do in class. For this activity, you are the HR director of a large private sector organisation. There is a well-established performance management system in place. Part 1. Using what you've learned about performance management systems in other units or units prior to studying HRM, answer the following questions about the existing system. What does it look like? Describe the existing performance management system. What is it used for? What kinds of decisions are based on information in the performance management system? Part 2. For the management and professional level employees in your organisation, assume that O'Boyle and Iguanas 2012 and 2014 are correct about the distribution of performance. What changes should you design into the performance management system? What changes should you make to the way decisions are made from that system, for example, in relation to rewards? for this case, this workshop, I was going to ask you to then present on part 2. Well done everyone. That's utility analysis in relation to job performance and value. Next week we have 2 more teams presenting, and I will also be discussing the benefits of better selection.